Good morning, class. Here's a short video on finding the initial conditions for an RLC circuit. In addition to the initial current, which we've done in the past, and the initial voltage across the capacitor, which we've done in the past, we need to know the initial conditions of the derivative of the current and the derivative of the voltage. Let's start with a little sample circuit here. We have a resistor, an inductor, and a capacitor, and a switch here that opens at time 0. So, following our previous examples, before time 0, and the circuit's been sitting there for a long time, the inductor looks like a short circuit in DC steady state. The capacitor looks like an open circuit DC steady state. So just before the switch gets thrown, we have our 12-volt supply and these two resistors. Okay, it's easy enough to find the current through the inductor. It's just 12 volts over 6 ohms gives us 2 amps. The voltage across the capacitor, because it's in parallel with this 2 ohm resistor, the voltage across the capacitor is equal to the voltage across that resistor. We do a simple voltage divider, and that comes out to be 4 volts. So now we know the initial current through the inductor and the initial voltage across the resistor, 2 amps and 4 volts. Remember those numbers, we're going to use them here in a second. Alright, now we need to find the derivative of the voltage at time 0 plus and the derivative of the current at time 0 plus. So, and here's the most important thing about this whole process. I'm going to redraw the circuit for time equals 0 plus. Right after that switch gets popped open, what do we have? So we have 12-volt supply. We still have our 4 ohm resistor. Now we know the current. The current right at this instant is 2 amps. It's going to change an instant later, but right after the switch gets thrown, we have 2 amps going through our inductor. We know the voltage across the capacitor right at this time. It is 4 volts. So now with this, we can do a simple circuit analysis and figure out what the derivative of the voltage is and the derivative of the current. Alrighty here. Okay, we know that to find dV dt, how much is the voltage in the capacitor changing? Well, IC equals dV dt. So that's a believe it or not. So we have the derivative of the voltage is going to be IC over C from this circuit. We know that since it's a series circuit, IC equals I equals 2 amps. So the derivative of the voltage at time 0 plus is 2 amps over 1 volts or 20 volts per second. I mean, when you make your circuit diagram and write it out like this, it seems nice and straightforward. Okay, now we need to know the derivative of the current with respect to time. Remember, for our inductor, V equals L di dt. So if we want to find di dt, we just need to know V sub L. So I'm going to do KVL, add up all the voltages around this loop, write that equation, and it should add up to 0. So what do we have? We have minus 12 plus V sub R plus V sub L plus V sub C equals 0. And there's our equation. In terms of current, we have minus 12 volts. Current times resistance, 2 amps, 4 ohms. For our inductor, it's L di dt. And the voltage across our capacitor at this instant is 4 volts. So solving this equation, that should be set equal to 0. I miswrote. Set that equal to 0. And if we solve that for di dt, we come up with 0 amps per second. So when you're solving these, when you're looking for the derivatives, draw the circuit out for time equals 0 plus, put in all the information you know, initial voltages, initial currents, and then you can just use your regular skills, your wonderfully developed circuit analysis skills to figure out what dV dt is and di dt. Thanks.